So we'll start the two-stage least squares notebook. The setup is always the same. We start by importing a bunch of modules. Then we set up the variables and the data sets so that this is completely generic. I continue to use the same example, the Chicago SDOH example. So you should have it loaded by now. So everything should be good to go. The modules are always the same ones, NumPy, Pandas, GeoPandas to get the data. And then from LibPySAL, I import very specific ones, just the ones I need. So open from LibPySAL IO, from the examples, get path to pull out the sample data, and from the weights, all the weights functionality. We don't need a lot of it, but I'm being lazy. I just import that. And then, so I don't have to write spreg dot OLS, spreg dot TSLS each time. I import these specific modules from spreg OLS as a reference, TSLS, which is two-stage least squares, and fstat, which is a F statistic on the joint significance of some coefficients. And that we don't really need that. I just have it in there to illustrate the Durbin-Wu-Hausman test, which, if you recall, is a test in an augmented regression. So we stick some extra variables in the regression, and we test the joint significance of those coefficients. We do that with an F-test. Okay, we use the usual stuff from Pandas, GeoPandas to read the data frame. We're going to do quite a bit of concatenation, where we will create new sets of explanatory variables by sticking the instruments in there and all that stuff, just to illustrate the different steps in two-stage least squares. LibPySAL, I mentioned the ones we use, and then the three from spreg. As usual, I start by setting up the input files. So we use GeoPandas. You can use Pandas if you read DBF file. No, you can't read the DBF file with Pandas. So you have to use GeoPandas for this. And then we create a kernel weights file. We will only need that for the functionality of the robust standard error. So you don't really need it per se for two-stage least squares, but since it's all in the same notebook, I do this here. So what did okay, I forgot to do the imports. So now this should work. And here we set up all the variables. So it's the same model again, the immigrant paradox model. So we have this bad health variable, so to speak, index of premature mortality, and the two ethnicity variables, Hispanic and Black, and then the poor economic circumstances, economic hardship index. And there's a whole bunch of different setups here, and let me go over them step by step. So the dependent variable is, again, this years lost. The initial specification that does not make a distinction between exogenous and endogenous variables is in Z names 1. So we have the three original variables. And then we have another specification, which I just threw in there to illustrate when you have more than one endogenous variable, but it's the same thing. So we have these same ones, but no high school diploma added on. So now we have 4 explanatory variables. And here we start separating out the exogenous ones from the endogenous ones and the instruments. The endogenous ones, first the exogenous ones, and those are the two ethnic variables. We keep those exogenous. The endogenous ones, the first example just has the economic hardship index as endogenous. The second example has the limited high school diploma also as endogenous. We have two sets of instruments. For the first example, we just have the X and Y coordinates as instruments. Those are kind of cop-out instruments without really thinking about it, because typically location is not something that is jointly determined by the system. So you throw it in there as an instrument. In the second example, I also add limited English proficiency as an additional instrument. So here we have three instruments. And then, as usual, we have the name of the data set and the name for the kernel weights, which we'll use later on. So we set that up. And then we actually, so this is always the way I set it up. Here is where you do the customization. So if you want to run this with your data set and your variables, this is where you change it. And then up here, everything is generic. So I don't talk about Chicago anymore. It's in file shape. I don't talk about the kernel weights anymore. It's in file K. And same with all these variables. It's Z, Y, Z1, etc. So this is totally generic. It will work with your example or with the example that you have here. So what I suggest you do once you have, and you should have, start to have a sense of what your project will be like, try this out. So just copy the notebook, keep the original one, and then just replace these variables and the files by, the in file, these files, and these variable names by what you want to look at in your project, and you don't have to change anything anywhere else. It all should work generically. If you want to change, of course, you can, but you don't have to. So this notebook lays out what I covered in class: the principle of two-stage least squares, concept of endogeneity. You replace the endogenous variable by an instrument. In instrumental variables, it's 1 for 1. In two-stage least squares, it's many for 1. And the many yield a predicted value in a regression of the endogenous variable on all the instruments. And so you run that regression, you get the predicted value becomes an instrument, and then you run instrumental variables. If you work it all out, you get this monster that I showed you in class, right? And but it's all basically an instrumental variable estimation, like right here, where H is the monster. Right? So the two stages, we're going to illustrate them now. The first stage, before we do anything, I'm just going to run OLS as a reference, so we know what the coefficients look like. We've done this a million times already, but just to have it in this notebook, it's always the same thing, same coefficients. They don't change. If they would change, something would be wrong, so there's nothing different here from what we did before. Now we're going to get the instruments. And so how do we get the instruments? We need a regression. We need a regression of the endogenous variable, and that's going to be EN1. There's only one in this case, on the instruments. And what are the instruments? Two things. The instruments are exogenous variables, XE, and I know this gets a little confusing, are instruments. So there's the terminology is kind of confusing. What is an instrument? What's an instrumental variable? It's all basically the same as long as you know the pure definition is 1 for 1, and two-stage least squares is many for 1, but in the end, it's the same thing. So what we need to do is we need to regress with OLS the endogenous variable, EN1, on all the exogenous ones, which we have in XE, as well as the instruments, the X and Y coordinates. The X and Y coordinates are in Q1. So to be able to do that, we have to put these are not together right now. They're separate. So one is in XE, the other one is in Q1. So we use the pandas concatenation command to slap these together. So now we have a new X matrix of explanatory variables that has the exogenous ones, the two ethnic ones, and the two instruments, X and Y coordinates. And these are slapped together in what I call here QQ. Now QQ becomes what we used to call X in the OLS specification. As a result, we now have a regression of the endogenous variable on all the instruments, and we get the results by printing the summary. And this is the summary. So obviously the R square goes up because we have no more variables. No, forget that. We have the endogenous variable as the dependent variable. We have the original exogenous variables, and then we have the two instruments. Everything is significant. The Y coordinate, not too much. Now, what does that mean in terms of the effect of location on economic deprivation? Remember, economic deprivation, if it's high, it's bad, right? High deprivation is high poverty. Low deprivation is low poverty. So some of you know Chicago. I know many of you don't, but this is negative. What does that mean? It goes down in which direction? In that direction, right? So, well, I'm mirror image. So the deprivation goes down from west to east. So east is better off than west. And here the deprivation goes up from south to north, which is kind of strange, but it's after controlling for everything else. You have to always think in multivariate regression, the interpretation of the coefficient is not what a bivariate coefficient would be, because you control for all these other things. So sometimes it makes total sense. Sometimes it doesn't make as much sense because it's whatever's left after you've already controlled for the spatial patterns in Black and Hispanic, right? And as we've seen, those are also highly spatially stratified in Chicago. So now we have our auxiliary regression, but we need the predicted values from this. The predicted values are an attribute of a regression object. If you recall the way this works in spreg, you first create a regression object. This has a number of methods, including summary, which gives you the nice printout, and a whole bunch of attributes that you can pull out separately if you wanted to. Like, typically you don't want to do this. The listing of the results is good enough. That's what you want. But if you want the betas, you can pull out the betas. If you want the predicted values, you can pull out the predicted values. And that's what we do here. We pull out these predicted values, and these are an array right now. This is some of the stuff you get in trouble with in Python and in NumPy in particular, keeping a good track of what is an array, what is a data frame. You can always go from one to the other, but you cannot use one necessarily for the other. So we have to create a new data frame where we turn this array into little pandas. It's actually not a frame, it's a series, it's just one of them. We give it a name. And then we're ready for the second stage. Now we have to do another concatenation where we take our same original exogenous variables, but now we tack on the predicted value of the economic variable. So not the original economic variable, but its predicted value from the previous regression. That is ZZ, once we slap those together. And now we run a new regression, the original Y, and instead of X, we have ZZ. So it's exactly the same as before. Before we had Z, and Z was Black, Hispanic, and the economic deprivation. Now ZZ is Black, Hispanic, and the predicted value of economic deprivation from a regression of that on Black, Hispanic, X, and Y. And this coefficients, these are the two-stage least squares coefficients. There's one problem with this. So you could say, oh, this is easy. I don't need to know anything. I just run OLS twice, which is correct. There's one catch here. The catch is that the residuals in this second OLS regression are residuals between the observed dependent variable and this weird ZZ, which is not the original Z, because it includes the predicted values of economic deprivation, not economic deprivation. So this is not really correct. As a result, the standard errors and the t-statistics and the p-values will not be really correct because they use the wrong right-hand side to compute the residuals. So even if you would do this in 2 steps, then you have to recompute the residuals and create the correct t-statistics and p-values. Now, of course, this is all done under the hood in TSLS. Not only do we need to know this about the predicted values and residuals, it's also a little bit, even if you use the original endogenous variables as the right-hand side, that kind of ignores the simultaneity. And so it's, again, a bit of an optimistic picture in terms of the fit of the model. So rather than doing these 2 steps, I just showed them to show the equivalent that is actually the same as the 2 steps. We now use the real thing. And for the real thing, we use the TSLS command from spreg. And the arguments for this are a little bit different from before. There are Y, that's the same. Only the exogenous variables are passed as X. So this is XE in our example. The endogenous variable is specified explicitly as Y and endogenous. The instruments are specified explicitly as Q. And I don't want any diagnostics for now, so I have to turn the non-spatial diagnostics to false because the default is true. Just like in standard OLS, the non-spatial diagnostics always pop out, right? And then, as before, we print a summary. So if we look at this, look at these coefficients. Let's just look at the last one, 153.58. This is exactly the same as what we had before. But look at the standard error, 36.905. And here it's 37.55. So it's not dramatically different, but it's different. So this is the way to do it. This gives you all the correct output. At the bottom of the table with the coefficient estimates, you have just to remind you what is deemed to be endogenous. and then what are the instruments that were used for this. Okay. And just to illustrate the case with the two endogenous variables, first the OLS results, or just to look at the different coefficients. So we have this no high school diploma added in here. And in two-stage least squares, we have the exogenous variables. We have the new, now there's two endogenous variables. Q2, there are three instruments. Otherwise, everything is the same. So if we run this, then we see here again, how different the coefficients are. So you see these, here is 67. When we take into account endogeneity, it's 324. Also, here, everything is significant except the high school diploma. Here, after we correct for endogeneity, the two ethnic variables are not significant, but high school diploma becomes significant, and the economic deprivation does as well. So the question then is this overkill, or should we just have stuck with, and should we just have stuck with OLS, or was there a real problem here? And remember, the logic of the Durbin-Wu-Hausman test is that if it was overkill, then there shouldn't be any difference, right? Then it basically shouldn't matter. I mean, you can do instrumental variables all you want. If you solve a problem that doesn't exist, it's not going to change anything, right? But if it does change things, then there was a problem. So we, in our particular example, have every indication that there actually was a problem because the coefficients are very different. And I didn't spend any time on it, but in the other case, the other example, it was the same. It was very different. So the DWH test is included by default when you use the default, which is non-spatial diagnostics true. Just like in standard OLS, if you follow the default, you get the test for heteroscedasticity, you get the multicollinearity condition number, you get the non-normality diagnostics. If you use the default in two-stage least squares, you get the Durbin-Wu-Hausman test. In this case, there's only one endogenous variable, 1 degree of freedom. The test rejects the null at 0.02. So there's some indication of endogeneity. In the second example, shall we run this again? It's even more significant. So there's even a stronger indication. And because we have two endogenous variables, the degrees of freedom are true, right? If you recall, the Durbin-Wu-Hausman test is nothing but a test on significance of the instrument if you add the instrument to the original regression. Again, if there's no problem, there shouldn't be any difference. That coefficient should not be significant. If you have multiple endogenous variables, you will have multiple instruments, and their joint significance, they should not be jointly significant. So in other words, if there is no endogeneity problem, adding those additional variables will not help you. You stick with the original coefficients. So their coefficients should be zero. They should not anything to the explanation if there is no problem, right? So we can now do a couple more concatenations to show this. So first, we already have this. This is our predicted value that we just created to illustrate the two stages in two-stage least squares. So now we're putting this together not with the exogenous variables, but with all of them. So Z1, if you remember, is Black, Hispanic, and economic deprivation, all three of them. And the null hypothesis is that economic deprivation is not endogenous. So therefore, if we add this predicted value, our instrument, its coefficient should be 0. It should not add anything to the explanation. However, if there is endogeneity, then that would not be the case. So we run this additional regression of y on ZZA, and you'll see in a second what this is. So this is the original setup with the predicted value from our extra regression added as a variable. And this is significant, right? If you have a good visual memory, you will recognize this p-value. This is exactly the p-value that we had here. Same thing. And if we now do an F statistic, now in this particular case, an F statistic is the same as doing a T statistic because there's only one coefficient to test for. And again, we have the same p-value. And this will be the square of this.
So this tells us that there is endogeneity.
That there is endogeneity, depending on your p-value tolerance. Now, however, in this case, so if you want to interpret something as being significant, I tend to set a very high bar, and my p-value tends to be 0.01, you know, depending on how many observations I have, maybe even smaller, right? But here, the logic is opposite, right? Here, we might have a problem. If we have a problem, we want to fix it. So we want to be careful, right? We don't want to overcompensate, but on the other hand, 0.02 is quite an indication that something may be going on. And as we saw, it does make quite a difference in the estimates in this particular example. That's not always the case, but in this particular example. So if you want to have fun, you can repeat this exercise and create the auxiliary regression with the two predicted, in the example, with two endogenous variables, you would have two predicted values from the auxiliary regressions. And then you would do the F-test, and the F-test would give you exactly what this gives you here in the Durbin-Wu-Hausman test. So it's a nice check for when you suspect there might be endogeneity. And in many cross-sectional regressions that use, particularly when you use census data, endogeneity is very prevalent because, I mean, Dobler's law, everything is related to everything else. So it's really becomes very difficult to separate out what is jointly determined by the system that you're trying to explain, and then what is truly determined outside that system. And in many cases, that becomes a matter of interpretation, or as I like to say, whoever screams the loudest, you know, calls something exogenous when it may not be exogenous, and so on. So my careful, advice is, if you have any doubt at all that something may not be totally exogenous, check it out. It's very easy to do, and it gives you a level of comfort.
What should determine